So now that we've established what mechanical advantage is and kind of how it works, I wanted to make a video discussing some details about mechanical advantage. Some of them might be obvious and some of them might not. But with that, let's go ahead and get started. And let's start with this incline plane or this ramp. And let's say this slope is about 12 feet long. And I want to give myself just a little bit of distance in between my measurement of 12 feet and the ramp itself. And hopefully that'll become apparent on why we do that in just a little bit. But we're saying that it's 12 feet long, and let's say that it's, let's keep the math simple. Let's just say that it's 2 feet tall. And what we're going to do with this ramp is we're just going to push a cart up it. And maybe we don't even push it up. Maybe we just hold it in place. It doesn't really matter. But let's start by saying, yeah, we're pushing it up. And we'll draw some guy, pushing it backwards. His legs are forward and his arms are back. He's holding it up. He's pushing it as hard as he can to push it up this ramp. Maybe it's super heavy, but the point of the ramp is to make it considerably lighter. It's a super heavy cart, and so he pushes it up the ramp, making his force effort much smaller than the force resistance or the weight of the cart itself. The weight is going to be a much bigger force than the effort that he pushes up the ramp, which is the point of using it. And we don't even need to know what these two numbers are right now. We just need to know that the effort force would be considerably smaller. And so we can calculate mechanical advantage using one of our two formulas. We've got our Ima-Deer equation and our AMA-free equation. And, since we're given two distances, I'm going to use our Ima-Deer equation. So we say Ima equals dE over dr, Ima-Deer. And I know it's silly, but it helps us remember. And since E comes before R, we know that dE goes over dr. And we look, well, which one of these two distances is clearly our effort? And, well, the distance our effort force would travel using our machine, that is our distance effort, which is clearly just 12 feet. And so that means our distance resistance, the distance we're trying to lift it up, that's the point of the machine. We push it up this ramp so we can get it up 2 feet. That's the resistance. That is 2 feet on bottom. And if we just divide these two, 12 divided by 2 is going to be 6, and feet cancel out. So we're just left with a mechanical advantage of 6. And so hopefully that's incredibly obvious. This system, if we use it, would give us a mechanical advantage of 6, which is why we'd use this machine. It makes our, well, not our work, but it makes our force 6 times smaller, essentially in theory. But now I want to ask a question. What if we don't use the machine completely? What if we use the machine a little bit differently than the entire length? So for example, what if we only went halfway up? So what if we only went halfway up the ramp here? So we stopped here at this point. So that's halfway up, which means we'd only go up 6 feet up the slope here. And if we draw it out, we draw this less than perfect line all the way to the end, that would only go a height of 1 foot. So how would this change our mechanical advantage? And so we still use our Ima-Deer equation. Let's write it out just to help us memorize. We say Ima-Deer, Ima equals dE divided by dr. And this time, our dE, our distance effort for only going halfway up, would only be 6 feet, whereas our distance resistance would only be 1 foot. And again, feet cancels out. 6 over 1 is still 6. So our mechanical advantage hasn't changed. And let's think about that for a second. No matter how we use this machine, just simple incline plane, this ramp, we're going to get the same advantage we would get from it. If we go halfway, the mechanical advantage is still 6. If we go a quarter of the way, we would just divide both of these numbers by 4, and we'd still get a mechanical advantage of 6 because it would still be proportional. So in fact, we can even write this out. We can write out this rule we've just established for ourselves. We could say, as long as the ramp has a constant slope, the mechanical advantage will be constant. So if the slope of the incline is constant, the mechanical advantage will be consistent. So the MA will be consistent. And that makes sense, right? If you look at it, no matter how we use this machine, it's going to be, the force effort is going to be smaller than the force resistance, even if nothing's moving, even if there's no work being done. Let's think about that for a second. What if this guy wasn't pushing up the ramp? What if this person was just holding it still? Well, I would argue that that force effort would still be smaller than the force resistance, and therefore we would have mechanical advantage. So even if there was no movement at all, even if just this effort force was there to cancel out the force of the cart, the weight of the cart rolling down the hill, since that would be smaller than our force resistance, there would still be mechanical advantage. So let's go ahead and write that out. Even if we had what we call static equilibrium. And I guess that is a new term, so let's go ahead and take a second to define that. We'll say where all forces cancel out. So even if there is static equilibrium, where all the forces cancel out, I would argue that our force effort is still less than our force resistance. And if our force effort is less than our force resistance, then by definition, there would still be mechanical advantage. So there would still be, mechanical advantage. And that might be a little confusing to think about. So let's write out an equation to show you how I know a force effort is smaller than our force resistance, which it would have to be. I would argue that it's very clear that the effort force that I'm holding this cart up with is much, much less than the force it would take to pick up this cart. That might be a little confusing on how that proves that there's mechanical advantage. So let's write that out. And let's use our other mechanical advantage, our AMA-free equation. And you got to say it again like a country singer. So AMA-free, like a country singer, AMA equals FR, free, is R becomes before E, so FR over FE. And so if we're using this equation, and we know that R, well, let's actually say, instead of FE is smaller than FR, let's say we know our FR is bigger than our effort force that we're applying, and FR is on top of FE. Let's think about that for a second. That means our mechanical advantage has to be greater than 1. Because if FR is dividing by FE, and FR is bigger than FE, then it doesn't matter what number you plug in for FR. If FE has a smaller value, which it would using this machine, you will always get a number greater than 1. Meaning you don't even have to be moving. You can be in static equilibrium with no work being done, and it's still possible to have mechanical advantage from a machine. Now, hopefully that wasn't too terribly confusing. In the next video, we will do another example with actual numbers for our AMA to explore this concept a little further.